Hello, ninth graders. We are moving on with I'm pretty sure, let me double check, the last lesson we have. That is true, the last lesson we have on factoring. So you've learned about difference of two perfect squares. You've learned about greatest common factor. You've learned about perfect square trinomials. You've learned about factoring regular trinomials. And you've learned about factoring by splitting. That's right. So when a is not equal to 1 was your last lesson. So when you have a number in front of your x squared, how do you handle that? We are now moving on to our last type of factoring, our last two types of factoring. So the very first thing we're going to talk about is the sum and the difference of perfect cubes. So it's very similar to the fact that with our difference of two perfect squares, we had two terms, each of which were perfect squares, and that they had a subtraction in between. So now we're starting to realize that it's pretty normal for us to have at least three terms when we're factoring, or three terms in general when we're factoring. So a nice alarm bell that should be going off for you is when there are two terms instead of three, and to do difference of two perfect squares. However, you can also have two terms that you factor out where both of them are perfect cubes. A cubed plus b cubed is the sum of two perfect cubes. And they could look like a lot of things. You can even see down below, we've got some perfect cube situations going on. But this is your general formula. It is equal to a plus b times a squared minus ab plus b squared. So that's the formula, where you've got this first term, which is cubed of this thing, plus a second term, which is cubed of a thing. And then you take those pieces apart and figure out what is a and what is b, and then you can put them into the formula like so. You have also got the difference of two perfect cubes, and it follows along very similarly with one or two few changes. Instead of it being a plus b, it becomes now a minus b. A way that I like to remember how to factor these guys is that these are the same. For your first term, the sign is the same between the two terms. So for your first parentheses situation, the sign is the same from the original guy to then this first piece right here. And then it follows along the exact same way here, a squared, except for it goes now plus ab plus b squared. So the difference between these two is just the signs, and they're just flipped around. So as a recap, if it's plus with your original guy, if it's a sum of two perfect cubes, then your first parentheses situation will also be a sum. If it's a difference of two perfect cubes, then your first sign will be a difference between the two terms, and then it's just the other sign for this middle term, the other sign. So then this will be minus, and then this will be plus. So try and write down a way for you to remember that these are the same, but then these are different. Some sort of way for you to write that out, and that these guys are always going to be plus. Always. Okay, so let's just practice it. So when we are first approaching a problem that looks like this, we need to first realize that there are two terms. So there should be an alarm going off somewhere in our brain that there are two terms going on here, which is pretty abnormal. So then try and look for, are they perfect squares? Are they perfect cubes? And here we'll notice that they are perfect cubes. So the first thing we should be doing with these types of problems, because the formula is especially hard, is we should be writing out what the formula is. So if this is the difference of two perfect cubes, we should go a cubed minus b cubed equals, remember that the sign, the symbol, the sign stays the same between these two on the first guy, and then it becomes a squared plus ab plus b squared for this second piece. So then the second thing that we need to do is label what is a and what is b. A is equal to the cubed root of that first term. If this is a cubed, then what is a? Well, the cubed root of a cubed. So the cubed root of x cubed is going to be just x. In order to find b, we need to take the cubed root of that second term. We do not need to take into consideration that this is a negative. We've already taken that negative into consideration with this difference formula. So what we should do then is just take the cubed root of 8, which is 2. Once we've gotten that figured out, we then do our formula. We take it all and plug it back into our formula. That is step 3, to revisit the formula. It becomes a minus b times a squared plus ab plus b squared. And this second term right here, although it looks like it could be factorable, unless it has like a greatest common factor, will never be factorable. This second piece right here will never be factorable. The first one might be. You have to double check if there's like maybe another difference or sum of perfect cubes, or maybe there might be a difference of 2 perfect squares. So definitely keep an eye out for that. Let's go ahead and move on to B. So this is 27x cubed plus 1. So this is 2 terms, 27x cubed and 1. So that should be an alarm bell of, oh, hey, we've only got 2 terms. I should probably be looking for something else that involves 2 terms. And you notice that these are perfect cubes. 1 is a perfect cube. 1 times 1 times 1 is 1. So it's a perfect cube. 1 is also a perfect square and a perfect fourth, right? 27x cubed is also a perfect cube. So I'm going to write out my formula. A cubed plus b cubed equals. It's going to be the same sign plus, and then a squared, and then it's going to be a changed sign here. A is equal to the cubed root of 27x cubed. You could always think about that as the cubed root of 27 times the cubed root of x cubed. The cubed root of 27, since it's positive 27, the cubed root will also be positive. And the cubed root of 27 is 3. And the cubed root of x is x. So the cubed root of 27x cubed is 3x. B is equal to the cubed root of 1. What is 1? Plugging it back into my formula, I get 3x plus 1 times. Now, be really careful here because that's that whole a term squared. So it's going to be 3x squared in parentheses. Don't forget that that squared has to go to both of those pieces. Minus, and then we can do 3x times 1 plus 3x squared. Simplifying it down, we get 9x squared minus 3x plus, ooh, not 3x there. That's my bad. That's 1. And that is your final answer. Okay, go ahead and do C on your own. So hopefully first you labeled out what is A. So hopefully you figured out that you have a greatest common factor here. If you did not take out the greatest common factor first, but you took a greatest common factor out at a later point, it ended up working out well for you. But you should definitely try and look for your greatest common factor first. So taking out your greatest common factor, you now have this situation. Remember that the 8 does have to stay there. It cannot go away. Now, A is going to be the cubed root of 8, which is 2, and B is going to be the cubed root of w to the 9th power. The cubed root of w to the 9th power, you can think of that as w to the 9th power to the 1/3 power. That raising an exponent, or turning a radical into exponent form just means it's 1 over that index. Or you can think of as dividing these two numbers out. Anyway, what you should be getting is w to the 3rd power. Now I'm going to take all this information and plug it into my formula for my sum of perfect cubes. The order does matter. So since it was a plus b, it becomes 2 plus w cubed times a squared which is 4, minus a times b, so 2w cubed, plus, and then w cubed to the second power is going to become w to the sixth power. Now go ahead and do d on your own. All right, with D, we do not have a Greaves common factor. We do have perfect cubes here. How we know that to the 12th power is a perfect cube and to the 6th power is a perfect cube is because they're divisible by 3. If you can divide these guys by 3 and get a whole number back, then that exponent does represent a perfect cube situation. A will be equal to the cubed root of a to the 12th power, which will become a to the 4th power. Remember that we divide those guys out in order to figure out what's left. And then b is equal to the cubed root of negative 729. Oh wait, no, sorry, not negative. B is equal to 729 b to the 6th power. So what we're going to do with that is the cubed root of 729 is 9. And the cubed root of b to the 6th power is b squared. So now we plug all this information in to our formula. So if it was a cubed minus b cubed, it now becomes a minus b times a squared minus a times b. Oops, I've run out of room. Plus b squared. So this becomes a to the 4th minus 9b squared times a to the 8th minus 9a to the 4th b squared plus, do not forget to distribute that squared to the 9 as well, so plus 81b to the 4th. Now this one is a tricky one because there is a difference of two perfect squares hidden in here. Two terms, perfect square and perfect square, and there's a difference in between. So that guy needs to expand out a little bit more. I'm going to write really, really tiny. And I have got a squared plus 3b times a squared minus 3b. Square root both of those first terms, or both of those terms, and put them on either side and have one that's plus and one that's a minus. And then I have a to the 8th minus 9a to the 4th b squared plus 81b to the 4th. That one was a really hard one. Good job.